We're now going to start doing some actual math here with these projectile motion problems. So we're going to talk about a few tips here, and then we're going to actually get into some of these problems. So the first thing is we're always going to split these problems into x and y. Just like we did with forces, we had Max and May. We're going to do the same thing with projectile motion, except it's going to be kinematics. Okay. Much like forces, any force and angle we broke into x and y components, so any velocity and angle we're going to break into x and y components. Since it is essentially kinematics, like we did in the beginning of the year, we're going to make two data tables, just like we did for kinematics with delta x and vi and vf and all that good stuff. The one thing to keep in mind is the only variable that doesn't have a direction associated with it is time. So time is going to be able to transfer from the x side to the y side and vice versa. Okay, so that's going to be the one variable that can go between the two sides. Alright, so for this first practice problem, the first thing I'm actually going to do here is draw a little picture. So I'm going to start with my stone here, which is thrown horizontally off of this cliff at a speed of 7 meters per second. And it's going to drop a distance of 50 meters before landing on the ground below. And so we're going to go ahead and set up everything we know in both the x and y direction. Now, there's two ones that we always know, and that is the accelerations. We know our x is going to be 0, and we know our y is going to be negative 9.8 meters per second squared. We also know our initial velocity in the x. We're told it's thrown at a speed of 7 meters per second, so that's our initial in the x. And we also actually know our initial in the y. Because we're told it's thrown horizontally, that means the initial in the y is 0 meters per second. The last thing we know is our y displacement. We start up here at a height of 50 and we end on the ground. Because we're losing 50 meters of height, our change in y, or our y displacement, is negative 50. Okay. We also could say that our final x is also 7. We know that that's going to be the same both in the beginning and in the end. So there we have our two charts set up. What we can do now is we can go ahead and solve for some things. Now we ultimately are looking for the displacement and the time. Over here on this x side, we really don't have enough information because the only equations we can use are the delta x equations, and both of them have time in it. So what we're going to have to do is we're going to have to go over to the y side initially and solve for some things using y information, and then we can transfer it over to the x. So I'm going to start with my delta y equation because I'm looking for time. I don't know VF, nor do I care about it. So my delta y is going to be negative 50. That initial term just goes away completely, and so I'm left with 1/2 times negative 9.8 times t squared. So I go ahead and I divide both sides by 1/2 times 9.8, or 4.9. I get 10.2 equals t squared, so my time then is going to be 3.19 seconds. So there's my answer for A. For part B, I'm thinking about how far we travel horizontally, so that's the x side here. So I'm going to go ahead and set up an equation using the information I have for the x. So we know it's got to be one of those delta x equations. I also know that my x acceleration is 0, so that part just cancels out. If you want to not write that every time, only to cross it out, that certainly is okay. So my x displacement is going to be my initial x velocity, 7, multiplied by that time, 3.19 seconds. And so I end up getting an x displacement here of 22.4 meters. Alright, we have a think about it question here. How long would a stone be in the air if it was just dropped from a height of 50 meters? We're going to go ahead and prove this answer mathematically. So I'm going to set this up like it's a free fall problem. So if it is a free fall problem, we know we're dropping it, so it has 0 initial velocity. Its displacement is going to be negative 50 because it's falling 50 meters, and its acceleration is negative 9.8 meters per second squared, of course. So I'm going to go ahead and solve for my time here using my delta x equation. My initial velocity here goes away, that entire term, since it's 0, and so I have negative 50 equals 1/2 times negative 9.8 times t squared. Many of you have probably figured out that this is exactly the same as the last situation, and so I'm still going to get a time of 3.19 seconds. This just mathematically emphasizes that idea that the vertical motion and the horizontal motion are independent of each other. It doesn't matter whether the stone is dropped or thrown at 7 meters per second horizontally. In both cases, we start with no initial velocity in the y direction. So in both cases, it's going to take the same amount of time to drop 50 meters regardless of what the initial velocity is in the x. So we're going to work through an example here of a horizontal launch, and then we'll do an angled launch. And we're going to find basically everything that we can find for this situation. So I'm going to start by setting up my two charts and going from there. So I know as always that my acceleration is 0 in the x direction. I know that my acceleration in the y direction is going to be negative 9.8 meters per second squared. I'm told that it's thrown at a velocity or launched at a velocity of 15 meters per second horizontally. So that's going to be my initial in the x, and because I'm not accelerating in the x direction, that's also my final in the x direction. Since it's a horizontal launch, I know that my initial y velocity is 0. That's always true for a horizontal launch. And I'm launching it here from a height of 25 meters above the ground. So I also know that my delta y for the whole thing is going to be negative 25 meters. I'm going to start with my y side here and find both the time, which is missing, and the final velocity in the y direction. Like I said, we want to find basically everything here, so I'm going to start with that. So when I sub in what I know, I have negative 25. That VIY term goes away because the initial velocity in the y is 0, equals 1/2 times negative 9.8 times t squared. And I end up getting that 5.1 equals t squared, so my time here is 2.26 seconds. I can also go ahead and solve for my final velocity. So for that final velocity, I'm going to use my VF squared equation. Again, I'm just using all these subscripts here to show that it's all for the y direction, but it's the same equation. So we have 0 squared plus 2 times negative 9.8 times negative 25, which means VFY squared is going to be equal to 490. So when I take the square root here, I get the VFY is going to be 22.1 meters per second, but I always need to do a plus or minus since that y velocity is going down, it's going to be negative 22.1. Moving back over to the x side, I'm going to go ahead and find my horizontal displacement now that I know my time. So I'm going to use my delta x equation. The acceleration term goes away because I have 0 acceleration, and so what I'm left with is delta x is simply equal to my initial velocity, which is 15, times my time, which is the 2.26, and so I get a horizontal displacement here of 33.9 meters. Okay, so now I can go ahead and start filling in some of the things that I know in my chart. So I know that my initial velocity in the y is going to be the 0 meters per second here. I just solved for that horizontal displacement, which was 33.9 meters. I know that when the object lands, its x velocity is going to be 15 meters per second because it's a constant speed. And the y velocity we solved for, that was the negative 22.1 meters per second. My time, I also know, was 2.26 seconds. So the one thing we have left to find now is this v and this theta. So v is the overall magnitude of my velocity when I land, and theta is the angle it makes. Luckily, I know my x and y components, so that's just going back to trig and Pythagorean theorem here. So I'm going to have an x component of 15 meters per second. I'm going to have a y component that I draw from the end of my x of 22.1 meters per second, and we want to find the overall hypotenuse, the overall magnitude, which is the hypotenuse, and the angle. So to get that hypotenuse, I'm going to do my Pythagorean theorem. So I have 15 squared plus 22.1 squared equals c squared. So I find that that hypotenuse there is going to be 26.7 meters per second. So that's the overall magnitude of my velocity. For the angle, I'm going to say that the tangent is equal to the opposite over the adjacent. So that means that tangent of my angle is equal to 22.1 over 15. And I find that my angle there, measured from the horizontal in this case, is 55.8 degrees. We have a drawing there, so we don't necessarily need to say south of east. We've already identified that the angle is this angle right in here. All right, so we don't necessarily need to worry about the directional, naming the direction. We just need to solve for the value of that angle. And so there we have those last two values, the magnitude of our velocity and our angle. So last thing to do here is draw the position versus time and velocity versus time graphs in both the horizontal and vertical directions. So in the x direction, we have a constant positive velocity, so my position versus time graph is just going to be a straight line with a positive slope. My velocity versus time graph is just going to be a horizontal line showing a constant positive velocity. In the y direction, we started some height above the ground, so I'm going to start up here. We were traveling down and also speeding up or accelerating down. So I'm going to have a line that's going down and getting slopier, meaning it's concave down. So my line's going to look something like that, okay, showing a negative velocity and a negative acceleration. For the velocity versus time graph, we started at a velocity of 0, and we have a negative slope and a negative velocity, so we're going to be going down while we're down here in the negative velocity region of the graph. So those are what those graphs would look like. We could label these times. It would be 2.26 here. This would be 25 is my initial height. This final position would be 33. But we don't need to worry about actually labeling them. The sketch and the shape is the more important thing. All right, we're going to do another find everything problem, except this time we're going to be doing it with a angled launch here. So I see that this object is being launched at a speed of 30 meters per second at an angle of 34 degrees. So the first thing I'm going to do is I'm going to go ahead and break that into x and y components. So that x component there is going to be 30 cosine of 34, and that ends up representing VIX because it's the x component of the initial velocity. The other component, VIY, is going to be 30 sine of 34. So that x component comes out to 24.87 meters per second, and my y component is going to come out to 16.78 meters per second. I can now go ahead and set up my chart in both the x and the y direction, and we'll go from there. So I know right off the start that my acceleration, the x, is 0, and my acceleration, the y, is going to be negative 9.8 meters per second squared. I just found my initial velocity, so in the x is going to be the 24.87 meters per second. That also happens to be my final, since we're traveling at a constant speed. In the y direction, my initial is 16.78 meters per second. So that's where I am right now. I'm actually going to go ahead and look at some of the concepts I know and actually start filling in some of the things that I know, because that's ultimately going to help me get another piece of information here. Right now I only have 2 things on the y side, and that's not enough. And on the x side, although I have 3 things, I need to use my delta x equation, so I need either displacement or time to be able to solve for anything on my x. So I'm going to go ahead and fill in on this chart what concepts I now know. So I just found my 2 initial velocities. So that initial in the x is going to be this 24.87 meters per second, and the initial in the y is going to be the 16.78 meters per second. I know that x is going to be the same throughout, so I can go ahead and fill in that x component for all the other locations because there is no acceleration in the x. I also here can actually fill in my y, so I know conceptually that at the peak that y velocity is 0, so I can fill that in. And on top of that, I know that when I return to the same point that it was launched from over here, I can put in my y velocity, and it's just going to be the negative of my initial, so negative 16.87 meters per second. So using one of these concepts, I can go ahead and get that other piece of information, in this case the y velocity either here or here, that's going to allow me to finish this problem. I'm going to go ahead and pick this one, so I'm really going to be thinking about going from here, from the beginning up to the peak. So that's the portion of the flight that I'm going to be thinking about. So I'll go ahead and use that final y velocity as 0 to solve for some other things. So I go ahead and make that final y velocity be equal to 0, and now I can solve for this delta y, which will be the displacement at the peak, and I can solve for the time. So using that VF equation, I can say 0 equals 16.87 plus negative 9.8 times t. And I go ahead and find my time there, and I get a time here of 1.71 seconds. So that's going to be the time at the peak here. I also can use the VFY squared equation to solve for my displacement at the peak. So 16.87, 0 squared equals 16.87 squared plus 2 times negative 9.8 times delta y. And I go ahead and solve for my delta y and get that delta y at the peak is going to be 14.36 meters. So once again, I'm going to fill in some of the things I know. I know my time here at the peak is going to be 1.71 seconds. I just solved for my delta y. That's going to be 14.36 meters. I also can fill in this velocity here. Okay, that's just going to be the magnitude of my overall velocity. So because the only velocity I have is in the x direction and there is no y component, that means my overall velocity is just this 24.87 meters per second. I'm now going to go ahead and solve for some things when I land and also solve for that horizontal displacement using what I know in the x direction. So two things I'm going to do. I want to know the time when it lands, and so I'm going to take advantage of the fact that this time at the peak is half the total, so I'm going to multiply that by 2, and I'm going to get 3.42 seconds, and that is the total time that the object is in the air. Okay, so that's the time that I'm going to use here with my x information to go ahead and solve for some things in the x direction. So I'm going to use my delta x equation. That second term goes away because my x acceleration is 0, and so I get the delta x is going to be 24.87 times that total time in air, 3.42, and I get an x displacement of 85.15 meters. Can now go ahead and finish filling in this chart here because now I know everything. So that x displacement I just solved for, that's going to be the 85.15 meters. I also found my time by just doubling my time to the peak. It was 3.42 seconds. I still need to find the magnitude of my final velocity and the angle. However, if I look carefully, these components and these components are identical, which means that my overall velocity when I land, that magnitude is going to be 30 meters per second. And the angle is going to be 34 degrees. The only thing that changed here is our y velocity flipped from being up to being down. So our hypotenuse, that magnitude, stays the same, but our angle is now 34 degrees below instead of 34 degrees above the horizontal. All right, moving on to our graphs here. We're once again going to sketch those graphs. So in the x direction, we're just going to have a straight line with a positive slope showing its constant velocity. And the velocity versus time graph is going to be a horizontal line above the axis, matching up with our position graph. We technically could draw both of them with a negative velocity, so it would be a negative slope here and below the axis, but I think it's easiest to just say it's traveling in the positive x direction. In the y direction, it's a little bit more complicated. We're starting down here now. We're not starting up at some height. And initially, we're traveling up but slowing down, so it looks something like this. All right, positive velocity but a negative acceleration. And then we start going down and accelerating down, so speeding up in the negative direction. Our velocity graph, we start with a positive velocity, but we're slowing down, so a negative slope approaching that 0 point where we stop, which is the peak there, and then we continue accelerating in the negative direction, meaning we have a negative velocity when we're on our way back down. So that's what those graphs would look like.